evening, everyone, and welcome back to 67 News, where we bring you the latest and greatest from the world of science. I'm Sebastian Barron, and today we're reporting live from the physics lab with a story that's all about motion, math, and a little bit of experimentation. Now, at first glance, you might not think much about launching a mini steel ball across the room, but in this experiment, that small launch helped us understand one of the most important ideas in physics: projectile motion. That's the curved path an object follows when it's launched into the air, all thanks to gravity pulling it downwards while its velocity pushes it forward. Our main goal in this lab is to figure out something called the muzzle velocity. That's just a fancy term for how fast the ball leaves the launcher. Once we know that speed, we can predict how far the ball will go and where it will land when it's shot at different angles, specifically shot from 30, 45, and 60 degrees. And to do this, we'll use a little bit of math and physics together. We'll measure things like the time the ball is in the air, how far it travels horizontally, and how high it goes before falling back down. With these numbers, we'll plug everything into equations that describe motion, equations that include acceleration, velocity, time, and distance. So basically, we're connecting the theory we learned in class to what actually happens when we perform the experiment. But of course, no experiment is perfect. We'll compare theoretical results which come from the equations to our experimental results, which come from what we measure in real life. The difference between those two tells us how accurate our setup is, and where small errors might come from. It could be things like air resistance, small timing differences, or even the angle of the launcher not being perfectly aligned. By running these multiple times and averaging our data, we can reduce those small errors and get a clear idea of how consistent our results are. And through it all, we'll be testing a simple but powerful idea that physics can predict motion with amazing accuracy, as long as we measure carefully and think critically about what we observe. So in short, this lab isn't just about firing a steel ball, it's about understanding how motion works, how gravity affects everything that moves, and how the math behind it can help us predict where things will land. And with that, I'll hand it over to my lab partner, who's going to walk you through the materials we used to bring this experiment to life.
Good afternoon, I'm Isaac, reporting live from the Physics 2420 laboratory. Today's top story, we're taking an aim at physics in motion, our mission to understand how gravity and velocity shape the curved path of a projectile. In this experiment, I worked with a mini launcher and steel ball to study projectile motion. The goal was to calculate the muzzle velocity, or how fast the ball leaves the launcher, and then we used that data to predict where it would land at different angles. We began to setting up the launcher horizontally to measure the muzzle velocity. By recording how far the ball traveled before hitting the floor, I used the formula t squared 2y divided by -a to find the flight time, and then vm equals x over t to calculate the initial velocity of the ball. Once that value was known, we adjusted the launcher to 30 degrees, 45 degrees, 60, measuring how far the ball traveled at each angle. Using our formulas for horizontal and vertical components, Vx equals Vm cosine and V equals Vm sine, we predicted the flight time and theoretical horizontal distance. Next, I compared those predictions to our experiment results, marking the landing spots on paper using carbon paper. After taking multiple shots for each angle, I measured the differences between the predicted and actual distances, then calculated the percent error using error times 100. From our data, we confirmed that the 45-degree angle produced the farthest range, matching what projectile motion theory predicts. Overall, this lab helped me visualize how the independent horizontal and vertical components combine to form a curved trajectory. It showed while air resistance is negligible, precision and setup are key to minimizing error. This is Isaac reporting from the physics lab, proving once again that in science, every launch is a lesson.
Coming up, I'm your host, Fernanda Torres, and I'll be covering Team 6-7's procedure of our sixth experiment. In this lab, we've moved on to projectile motion. We used a mini launcher that shoots a steel ball to calculate landing positions at different angles. We calibrated all the equipment and made sure everything was running. The first part of the experiment, we shot the ball at 0 degrees, so it laid flat. We launched the ball 5 different times, then measured the average distances from the launch point on the floor. We then calculated muzzle velocity using the given formula. Now, this is us in action. Here is us launching the ball 5 different times, and you can see that the ball hit the carbon paper on the floor, which we then removed to reveal the regular paper on the bottom, where it showed exactly where the ball landed. Now this is us measuring the distances. For the second part of our experiment, we shot the ball at different degrees. We did one at 30 degrees, 45 degrees, and 60 degrees. We also shot the ball 5 times for each of those degrees that we did. This allowed us to calculate the theoretical and the experimental differences to find the percentage error within those 3 degrees. Now, this is us in action. We set our first degree to 30, and this was that launch. Now this is the launch for 45 degrees. Then lastly, 60 degrees. As you can see, this lab was able to guide us through a great representation of projectile motion in a fun way. Testing out the different angles and seeing how the carbon paper transferred the ball impact was fascinating. There is physics in absolutely everything. Thank you for having me this evening. Now I'll pass it to my teammate that will go into more depth on our calculations. Good night.
Hello everyone at home on this cold October evening. I'm your co-host, Mateo Barasa. I hope everyone's staying inside, staying warm, has their jackets on. And this evening we have something different from the students down at the lab at UTEP. Instead of the traditional graphs and the track with the frictionless system, we are now going to be observing a mini cannon, a mini projectile launcher, so to say. So the students were using this projectile launcher that had steel balls, and it was put at a different angle each time to calculate just how far this ball will go. So the experiment is used to emulate the independent variables that affect a ball's trajectory when it's launched. So in this case, we had the projectile shift the angles from 0 degrees, 30 degrees, 45 degrees, 60 degrees, and then finally 90 degrees. And each time we guessed how far the ball was gonna go and just how much the trajectory changed how much the angle changed the steel ball's trajectory. So to start, we first tried to find the initial velocity, which is shown by this example right here. We use our initial given values to finally find out our v of x, which is the trajectory, and it's found using this equation right here. And then once we had that, we then calculated our results changing theta, which was 30 degrees, 45 degrees, 60 degrees, and finally 90 degrees. So just about here. So this took students a long time, almost, because there's a lot of error having to do with the angle and getting the trajectory right each time and keeping it consistent in close, compact patterns. So each time there were some issues with that, but trial and error, and eventually we were able to get our percent value down to a low value. And our results are shown right here. And the instance that it went the furthest and the air travel was the longest was going to be this one right here. And that's shown by the values in our table. So all in all, it was a pretty awesome experiment, and our results are very practically used in our daily life. See, for instance, when someone throws a football, the angle that'll maximize the distance is somewhere between 40 and 45 degrees, and that's shown here. So again, thank you guys for looking over this data with me, and I'll catch you guys next week, next evening at this exact time. Thank you guys so much, and I'm gonna pass it on to my co-host, Oliver Amasquita.
Good evening. I'm your host, Oliver Amasquita, and welcome back to Late Night 6-7 News. Tonight, Team 6-7 takes aim at our most explosive experiment yet, projectile motion. In this lab, we used a mini launcher to explore how gravity shapes the curved path of a projectile. Our mission was to calculate the muzzle velocity, the speed at which the steel ball leaves the launcher, and then predict how far it will travel at different launch angles. So using the launcher and a bit of algebra, we calculated our muzzle velocity to be about 3.294 meters per second. So we started by first firing the launcher horizontally to determine that velocity, and then we ran trials at 30 degrees, 45 degrees, and 60 degrees, calculating the theoretical landing positions for each one. So we did 5 shots for each angle, and we used a carbon paper to mark where each shot actually landed. And then we used a meter stick to measure the actual distances. Then came the fun part, comparing those landing points with our predictions, the theoretical ones, to find the percent error for each angle. Our results were impressive, actually. At 30 degrees, we recorded a percent error of about 1.2%. At 45 degrees, the error dropped slightly to 1%, which is a near perfect match between theory and reality. But at 60 degrees, the percent error jumped to around 14.6%, likely due to a steeper trajectory, increased airtime, probably more air resistance, and maybe launcher inconsistencies. Interestingly, the 30-degree angle gave us the farthest distance overall, slightly outperforming the 45-degree angle, which is often considered the ideal launch in theory. This real-world result reminded us that factors like friction, launcher precision, and even subtle variations in how the ball leaves the barrel itself can actually shift the outcome. So to finish things off, we took on the extra point challenge, where we had to predict and hit a specific target just based off of our intuition, and Team 6-7 nailed it, unsurprisingly. Overall, this lab showed how breaking motion to horizontal and vertical components makes projectile motion easier to understand and accurately predict. It also reinforced how even a small percent error can tell a big story about accuracy, precision, and the limits of real-world experiments. Overall, that wraps up tonight's coverage on Team 6-7's Lab 6. I'm Oliver Mesquita, signing off from Late Night 6-7 News. Thanks for tuning in, and we'll see you in the next lab.